Okay, welcome to everybody to the lockdown version of our next lecture. So last lecture we finished the MSO algorithmic meter theorem for tree width, briefly talked about clique width, and then started focusing on first order logic, which the next part of the lecture will be about. So first we're going to wrap up with first order logic, in particular with Ehrenfeucht-Fosé games, and then we're going to talk about model checking, finally, on bounded degree graphs. So we briefly introduced Ehrenfeucht-Fosé games already, and there were means to show that things are not expressible in first order logic. So for example, if we want to decide or want to show that you cannot express connectivity in first order logic, how would we do that? First, we said that two structures G and G prime are Q equivalent if all first order logic formulas or sentences of quantifier rank at most Q are either both true or both false, true on both structures or false on both structures. So they cannot distinguish G from G prime. And then we're going to show that for every Q, there will be a graph G that is connected and G prime that is disconnected, and they will not be able, and there will be Q equivalent. And assuming now there was a formula to show connectivity, then this was had some fixed quantifier in Q, and this formula cannot tell G and G prime apart because they're Q equivalent. That's our contradiction. And how are these games defined that we're going to use to show Q equivalence? So for every Q, there's an Ehrenfeucht-Fosé games on Q rounds, and it's played between a duplicator and a spoiler. And the spoiler is going to pick elements in G or G prime, and we're going to call this elements G1, G2, and so forth. And the duplicator corresponds with the element in the other structure. So if the spoiler picks G1, the duplicator corresponds with G1 prime, and if the spoiler picks G2 prime, the duplicator corresponds with G2, and the duplicator tries to copy the moves of the spoiler as well as possible. And the aim of the duplicator is to make sure that two elements are connected in G, if and only if the corresponding elements are connected in G prime. So Gi and Gj should be adjacent in G, if and only if Gi prime and Gj prime are connected in G prime. And if this is still the case after Q rounds, then we say that the duplicator wins the Q round Ehrenfeucht-Fosé game. Here in this example, we just lost it because we need to find an element G3 prime that is connected to G2 prime, and there is no such thing. No matter where it picks it, it will not be connected to G2 prime. So the duplicator has lost the game here, but of course the duplicator could play a little bit smarter, like copy the moves like this, and maybe here. But even then, after I think 5 rounds, will not be able to pick a G5 anymore that is not adjacent to any of the previous vertices. So if it picks G5 here, then it will be adjacent to G3, but G5 prime and G3 prime will not be adjacent. So here the duplicator lost. And of course the duplicator has to lose at some point because the structures are not equivalent for every Q. And the theorem says that two structures are Q equivalent if and only if the duplicator wins the Q round Ehrenfeucht-Fosé game. Okay, so far so good. Then let's put this theorem to use. So first, we can use it to show that first order logic cannot decide connectivity, parity. So for every Q, you can create a graph G and a graph G prime, such that G has an even number of vertices, G prime has an odd number of vertices, and that they're Q equivalent. And after we've shown this, it follows that first order logic cannot distinguish between graphs with even and odd number of vertices. And the way we're going to construct these graphs is very trivial. So G is going to have q plus 1 isolated vertices, and G prime is going to have q vertices, all isolated. And now the strategy is also very trivial. If the spoiler picks some element in G, the duplicator corresponds with an arbitrary element in G prime. And similarly, if it picks an element in G prime, the duplicator corresponds with an arbitrary element in G. And since there's q elements, at least in both structures, we never run out of elements to pick as a duplicator. You can always pick a next one. And let's say after q rounds, these elements have been picked. We notice that all the orange elements are disconnected, and all the purple elements are also disconnected because everything is disconnected with this graph. So the duplicator has won this game after q rounds, which means these two structures are q equivalent.
We just have to come up with one instance, or one such pair of graphs, G and G prime, such that they can't be distinguished.
Exactly. You only need to come up with one such pair that cannot be distinguished, and this is a contradiction to the claim that every pair could be distinguished. Okay. And yeah, this parity is now a very simple example. And next, I would like to talk about a more complicated one. This is going to be about connectivity. Also, connectivity cannot be expressed in first-order logic. There's no formula that can tell connected graphs from disconnected graphs apart. And how are we going to show this? We're going to pick a q and then create a disconnected and a connected graph G prime that are q equivalent. And these two graphs look like this. So G will be two circles that are disconnected, and each circle has 4 to the q vertices. And similar, G prime will just be a single circle that is connected, and it also has 4 to the q vertices. Obviously, G is connected, G prime is disconnected, and we will show that after q rounds, the duplicator wins the Ehrenfeucht-Fusee game after q rounds. And first, let's start with some intuition on how the duplicator could win the game. So the spoiler picks some element in G, for example, and then the duplicator corresponds with another element in G prime. So far, the elements in G prime, they all look the same, so it doesn't really matter which one to pick. And now, if, for example, the spoiler picks an element that is very close to an existing element, for example, it has distance x, then the duplicator picks an element that also has distance x. So if the elements are very close to each other, then we need to copy it very exactly. It should have the same distance then. But what if the spoiler picks an element that is very far away from the existing elements? Then we have a lot more freedom. Then we can just pick an arbitrary element that is also very far away from the elements that we've chosen so far. And now we notice that here, these vertices are disconnected in G, but they're connected via this path in G prime. But since the distance is very large, the spoiler will not, like if the spoiler were trying to prove that these vertices are connected here via some path, it would have to pick a lot of vertices along this path. But the distance is so great that the spoiler cannot prove that they're connected. And so this is intuition, and it continues for q rounds. And let's maybe formalize a little bit of what the strategy is going to look like. So we're going to build a proof by induction. We're going to define our strategy for the duplicator inductively. We assume that we have a strategy to pick the first I elements, and then we're going to turn this into a strategy that picks also the I plus first element. And the induction hypothesis that we want to maintain at all times is the following. We want to show that the duplicator can play such that after I rounds, when the elements Gi to G1 to Gi and G1 prime to Gi prime have been chosen, that then the distance between two vertices in G is the same as the distances between the vertices in G prime for all pairs Gi, Gj, and Gj prime and Gk prime. But here, you notice there's a subscript here in the distance measure. And this means that the distances only need to be the same up until some threshold value. In this case, 2 to the q minus I plus 1. So either they're both the same, or they're both larger than 2 to the q minus I plus 1. So in a sense, values that are larger than 2 to the q minus I plus 1, they get rounded up to infinity in this distance measure. And so what does this really mean? It means in the beginning, when I is maybe 2, then we have 2 to the q minus 1. So then in the beginning, when I is 2, the first two elements, the distances need to be mapped very accurately. There's the threshold value is very high, it's 2 to the q minus 1. So up until this value, we need to preserve distances in the other structure when we place a duplicator. However, later on, when I is equal to q, so in the very last move, then the distances need to be exact only up to 2 to the q minus q plus 1, which is 2. So they only need to be accurate up to distance 2. So either they have the same distance or the distance is larger than 2. And in the end, this is enough. So we only need to make sure that they're adjacent in the one structure, if and only if they're adjacent in the other structure. And if the distances match up until distance 2, then this implies what we're trying to prove. So far, so good. If yes, then let's show how the strategy actually works. So we assume that we have already picked the elements up until gi, and now we want to pick the I plus first element. And we're going to make a case distinction. So the first case is that g plus 1 is close to other vertices that have been picked already. So in this picture here, we have this element gi plus 1, and we have this gray area, which is the radius within which we have to map distances exactly to the other graph. So here we mark the gray area that has distance at most 2 to the q minus I from our vertex g plus 1. And let's assume that there's some vertices already in this gray area. Then it follows that the distance between any two vertices in this gray area is at most 2 to the q minus I plus 1, because the distance between any two is at most twice the radius. So it is 2 times this number here, and that is 2 to the q minus I plus 1. And now we're going to use our induction hypothesis. And the induction hypothesis states that in the other graph so far, there have been chosen some other elements, and their distances have been preserved exactly up until the threshold 2 to the q minus I plus 1. And any two vertices here and here, their distance is bounded by 2 to the q minus I plus 1, which means they have exactly the same distance in our purple graph on the right. And this is very nice. So it means that this gray area, it occurs in the other graph in exactly the same way. So these 4 vertices with the same distances have been inserted there already. And what we can then do next is we can put our element g plus I prime into the same spot of this figure that we see already in the graph. And this only works because we're decreasing this distance threshold. So that is the first case. And the second case is what happens if the element that we chose, or that the splitter chooses next, the gi plus 1 is not close to any other vertices. So as we see here in this picture, there's no other orange vertices within the gray area. Then now we're going to use the fact that our circles are rather large. Then there will be, because the circles are so large and we've only chosen I vertices, and the gray areas are also relatively small, there will be some free interval here on the other graph. And within this free interval, we can place our vertex gi plus 1, g prime I plus 1. So this is now where we exploit the structure that the fact that the circuits are large enough that there will always be a free slot somewhere. And this finishes case distinction. And yeah, other questions up until now about this proof? So this is how you can show that the duplicator cannot or wins the game for these two circles. And yeah.
Sorry?
Yeah. Yeah, you go first.
Where the 4 to the Q comes from.
The 4 to the Q was chosen such that I can always pick, like in the second case where gi is not close to other vertices, I can always pick the gi prime, gi plus 1 prime somewhere else that is not close to other vertices. So I didn't show the math, but the math will work out and there will be this free slot somewhere. Okay, there was also an online question.
Oh yeah, maybe two more basic questions about these games. One, does the spoiler always need to pick in one graph? Like if it picks in one graph, does he always need to pick in this graph, and the duplicator always gets to pick in the other graph?
So the spoiler can pick in an arbitrary graph, either G or G prime, and the duplicator has to respond in the other graph.
Okay, so I guess then, does it change these games if you take away this ability? If you force him to always pick in one graph, or?
Yeah, I think this will change the game.
Okay.
For example, if the graph only has a single vertex, then the spoiler could only pick a single vertex in this graph. And
oh yeah, sure. Okay, so that basically asks the second question, which is, do these graphs need to have the same size? Which apparently they don't.
No, they don't need to have the same size. Like with this example here, here for the parity, specifically one vertex has Q plus 1 vertices and the other one has Q vertices. So this means there's a graph odd number of vertices that cannot be distinguished.
Okay, so then I guess the ability of choosing in either graph is what would destroy, because I was thinking, why not just pick one graph and then for the second graph copy it, so you have two copies of that are disconnected, so you can always basically just have the same graph effectively, but you also have it twice and you don't really touch it. But if the spoiler can choose in either graph, then maybe that's where the problem comes in. Yeah.
Any other questions? If not, then I wanted to show another application of Gaifman, of our duplicator spoiler games that maybe becomes a little bit surprising. You can also use it to prove Gaifman-Ward theorem. So we're going to focus on the case of first order logic and disjoint graphs. So now we have two graphs F and H. We're going to show that the Q type of the union of F and H is completely determined by the Q type on F and the Q type on H. And again, the Q type of a graph is a set of all first order sentences of quantifier rank at most Q that are true in the graph. And the connection to our Ehrenfurcht-Rosé games is that two vertices have the same, two graphs has the same Q type if and only if they're Q equivalent. So instead of Q types, we can also talk about the equivalence of two graphs. And then, using this different formalism, the statement reads as follows. So we're going to have two graphs F and F prime that are Q equivalent, and graphs H and H prime that are Q equivalent. And Gaifman-Ward says now that the Q type of F union H is the same as the Q type of F prime union H prime. So these two graphs should also be Q equivalent. So in other words, if I take F union H I swap out F with something that is equivalent, and I swap out H with something that is equivalent, the Q type stays the same. I get something that is equivalent to the original graph. And the proof of it is actually quite short. So we're going to use our winning strategies of a duplicator. So F and F prime are Q equivalent. So there exists a strategy as F for the duplicator to win the game. Let's call it SQF to win the Q round Ehrenfeucht games on F and F prime. Similarly, H and H prime are Q equivalent, which means there exists a strategy as HQ for the duplicator for the game on H and H prime. So if we look at only the blue part or only the red part, there we have a strategy for the duplicator to win. But now we need a strategy for the union of the two graphs. So we need a strategy for the duplicator on the graph F union H and the graph F prime union H prime. And what we're going to do is we're just going to play according to the strategy as F and as H, depending on where the vertices are picked from. So if a vertex, maybe H1 is picked here, then the strategy for H gives us another vertex H1 prime in this graph. Similarly, if maybe a vertex F1 is picked here, F1 prime, and the strategy for the graph F gives us a move to pick a vertex F1 here. And it continues like this. So if H2 is maybe chosen here, then we can choose another H2 prime, and they're connected if and only if they're connected in H if and only if the corresponding vertices are connected in H prime. You can continue here as well. Here, maybe another element is chosen here, another element is chosen here. And now we notice that the connections between here and the connections between here, they're all, and here, they're all trivial connections. They're always non-connections. So, and this means that if I take the union of these elements, so if I take these 5 elements and these 5 elements, they're connected in exactly the same way. And this is exactly what we need to make sure of to show that we have a strategy for the duplicator. So, yeah, this already completes the proof. So because the connection between F and F prime and H prime is always non-connections, we notice, for example, that this element here and this element here are non-connected. And we need to show that also in the other structure, the corresponding elements are non-connected. And this is the case. So this element here and this element here, they're also non-connected. Okay, so this is a very concise way to prove the Pfefferman-Watt theorem, at least for first order logic. But we haven't mentioned yet that the Q type is computable from the Q types of F and Q type of H. For this, you have to do something else. But if you just want the base version without the computability, then I guess the proof is this short. And so as a summary so far, we noticed that first order logic is quite well as capturing some kind of problems, like independent sets or dominating sets or cliques, but it fails quite hardly for example, connectivity or parity. So these basic tasks, which you would expect that they should be easy, they're actually quite hard. But if you want to fix this, there's also extensions of first order logic with parity or with counting or with fixed points. They tend to capture like more of these seemingly simple problems. But then model checking is hard for these logics probably. So the more expressive the logics, the harder the model checking problem for them. That's why we're gonna only consider the case of first order logic in this lecture from now on. But yeah, if you're interested in this, there's a whole field of descriptive complexity, which deals with expressiveness of various logics. And yeah, this brings me to the end of our excursion of first order logic. If there's questions about it, now's the time. If not, we can finally turn to the algorithmic aspects of it. So I now want to prove the first order, or the first order meta theorem. It was by Caesar originally, and it is for graphs with bounded degree. So the flavor of it is very similar to Excel theorem. We again get an FPT algorithm, at least this time for bounded degree graph classes. So the statement is we have a graph class C with bounded degree, and then there exists a function that's going to be a runtime bound, and it depends on C. And you can evaluate first order formula phi on a graph G from the bounded degree graph class in FPT time. So the running time will be some function of the length of the formula times n. So in particular, every fixed formula can be evaluated in linear time. So every problem expressible in first order logic can be solved in linear time on bounded degree graph classes. Okay, so this is a statement that we want to prove. And this then shows that bounded degree graph classes are tractable. And we're gonna, the same method, we're gonna use it later on also for locally bounded tree width graph classes. And locally bounded tree width will generalize basically everything that we've talked about so far. It generalizes bounded tree width, planar graphs, bounded degree, forests. So locally bounded tree width will be a very, very general measure of sparse graphs. But first, let's talk about the bounded degree case, because everything will translate quite easily once we have done the bounded degree case. And assuming we have solved this problem, then we can solve a bunch of problems in running time f of k times n on bounded degree graph classes. And the example we've talked a lot about already. Of course, you can find an independent set of size k in this running time by just writing down the formula for it. Similarly, you can find a dominating set of size k in time f of k times n. How about finding a k times k grid? This can be done the same, quantify over the vertices of the grid, and then say that there should be connections between all vertices of the grid. So it's also possible in first order logic. Well, can you decide whether a graph is connected? I mean, you can do it in this time, but not using first order logic. So here, this meta theorem does not give us an answer. Or how about finding a set of size k that dominates half the vertices of the graph? This is something you can do with this meta theorem. So before we had some kind of intuitive understanding that it probably doesn't work, but now we can actually prove it. So let's take this graph here. Q vertices here, Q plus 1 vertices here. And we'll take a different graph. It looks like this. Q plus 1 vertices here. Q isolated vertices here. Now we notice in this graph, this vertex here dominates half the vertices of the graph. And in this graph, it doesn't dominate half the vertices of the graph. So we're going to call this graph G, this graph G prime. And you can create a simple Ehrenfeucht-José strategy for the duplicator, which proves that you cannot distinguish G from G prime using Q rounds. And yeah, for every Q, you can make this construction. So now we have a proof that you cannot express the problem, is there a set of size k that dominates half the vertices? You cannot express this in first order logic. So the answer to this is also no. And let's talk a little bit about techniques that we're going to use to prove this theorem. So we're going to split it into two parts. First, we're going to show that it is possible to find things that are sufficiently far apart, both so where the requirement is that things should not be connected, like independent sets. And also we're going to show how to find things that are local, like connected subgraphs or cliques, like they only are within a small region, if they exist. And then we're going to combine these two things. So there's a very famous theorem by Gaifman, which states that first order logic, in a sense, can only express local and global property. So you can define, you can decompose the first order model checking into these kinds of local and global things. And this is how we're going to solve it. So this will be a bit more formal later on, but first we're going to introduce, we will introduce the logical parts only in the end, and first get a bit of intuition about it first. And afterwards, we're going to lift it to locally bounded tree width. So let's talk about our main tool that we're going to use. And it's a very simple tool. It just states that local subgraphs in the bounded degree graphs are relatively small. So if you have a vertex v in a graph with degree at most d, then the R neighborhood of this vertex has size at most d to the R plus 1. And by R neighborhood, I mean every vertex that has distance at most R from v. So R neighborhoods in bounded degree graphs are small, is what the statement means. And you could probably already expect the proof. So the way you could formalize it will show that there's at most d to the I vertices with distance I from a vertex v. And then if you sum up all the vertices with distance 1, 2, 3, 4 up to R, then you get this bound of the neighborhood, show that the neighborhood is bound at most sum over I d to the I, and this is bounded by d to the R plus 1. So now we need to only bound the number of vertices with distance I. And if I is equal to 0, then this is of course true. So there's only a single vertex with distance 0 from V, which is V itself. And then if you go outwards, it can only grow by a factor d, because every vertex with distance I plus 1, it needs to be a neighbor of a vertex with distance I. And every vertex with distance I can at most d many outgoing edges. So this neighborhoods, they can only grow by a factor of d in each iteration. And this shows that there's at most d to the I many vertices with distance I. And it also shows this bound on the size of the neighborhood in bounded degree graphs. And now it's time to prove our first logarithmic tool that we're going to use later on. So I want to show that you can find so-called R scattered sets of size k in a graph of bounded degree. And here's a picture what an R scattered set is. So an R scattered set is something like a generalization of an independent set. In an independent set, every vertex has distance larger than 1 from each other. And here we want k vertices that pairwise have distance larger than R from each other. This is what we call an R scattered set. And additionally, to make it a bit more interesting, we assume that some vertices of the graph are red, and that our R scattered set should contain only red vertices. And our graph has degree at most d, and the statement says that we can find an R scattered set of size k in time f of r comma k times n. on bounded degree graph classes. So it will be more of an f of r k d times n if we assume d to be the bound on the degree for a graph class. Okay. And let's first talk about a simple case that there is at most d to the r plus 1 times k red vertices. So the number of red vertices is bounded by d to the r plus 1 times k. Then we can use a simple brute force algorithm. So we enumerate every subset of k vertices that is red. So there's like d to the r plus 1 times k, choose k, such subsets of k vertices, and then we check whether they're red. And this is all we need to do in this case. We can use a brute force, and this is now a function of d, k, and r, and everything is fine. So it gets more interesting if the graph is larger. If we assume that there's more than d to the r plus 1 k red vertices in the graph. And what can we do then? We're going to do a simple greedy algorithm. So we'll pick a single red vertex and put it into our r-scattered set. And this is going to be the first vertex of the r-scattered set. And what does it mean? It means every vertex with distance at most r from the red vertex, it cannot be added to the r-scattered set anymore. So if there's a vertex that is red and very close to v1, then the distance to v1 is smaller than r, and it cannot be added anymore. So what we can do now is we remove every vertex that stands in conflict with v1. And this is exactly the r neighborhood of v1. We remove it, and this removes at most d to the r plus 1 vertices of the graph, which means the number of remaining vertices that are red are at least d to the r plus 1 times k minus 1. So before it was times k, now it is times k minus 1, because we removed d to the r plus 1 vertices. And this is something we can repeat now. We pick another vertex, and the number of red vertices is still at least d to the r plus 1 times k minus 2, or times k minus 3 after picking 3 vertices. So in the end, this means we can pick k vertices, and at all times there were still red vertices to choose from, because we didn't remove too many of them. And so a simple greedy algorithm works in this case if the graph is large enough, and if the graph is small enough, we'll do a simple brute force algorithm, and in either case, the running time is fine, and we solve the problem efficiently. So this is a very nice duality argument, I think. And it shows us how to find things that are relatively far apart, like r-scattered sets. And the other ingredient that I want to mention was things that are close to each other. So now I want to show that you can decide in time f of k times n whether a graph from a bounded degree graph class contains a k by k grid as an induced subgraph. And the k by k grid is local because it is contained in only small neighborhoods of the graph. So the picture kind of looks like this, with a graph of degree at most d, and we're interested in whether there's a k by k grid as an induced subgraph. And we notice that this k by k grid, it has diameter at most 2 times k. And what does it mean? That if we have a Just instance, if there is a grid, then it needs to be contained in a neighborhood that is, this is a bit wrong, and 2k of some vertex v. So it needs to be contained in a 2k neighborhood of some vertex. And we also know that the neighborhoods of every vertex are reasonably small. So within the neighborhoods, we can do a brute force search. So we need to find a k by k grid in a neighborhood of size in the 2k neighborhood of v, and this can be done in neighborhood size to the O of k squared, because we need to place the k squared vertices of the grid somewhere, and we can guess all combinations. And this is a bound on the number of combinations. And additionally, we know that this neighborhood size is bounded. It is at most d to the 2k plus 1. So in total, the running time is bounded by this function here, neighborhood size to the k squared. This is a function of d, k, and yeah, that's all we wanted to prove. So now we use the fact that the grid is contained within a small region, and small regions have contained within a region with small radius, and regions with small radius have small size, so we can brute force on every such region. And as a homework, we will show how to combine these ideas to not only find grids, but find arbitrary induced subgraphs. So I'm going to show how to check whether a graph has h as an induced subgraph in time f of h times n. And if h is, for example, an isolated set of vertices, then this amounts to finding an independent set of size 6 in this example, because we need to find these 6 vertices as an induced subgraph. That's an independent set. Or if they're all connected, then this is the same as finding a clique of size k in a graph. And yeah, I'm going to talk about this later, hopefully. I wanted to focus on the little bit simpler case first. So now we want to decide whether a graph contains 2 disjoint k by k grids as induced subgraphs. So not only a single grid should be contained as a subgraph, there should also be a second grid somewhere. And these 2 grids, they should not overlap. And so in the way, each of those grid is a local property, but the property that they need to be disjoint, that's the property that kind of enforces things to be far apart of each other. And this is how we're going to see it. Yeah, 2 disjoint k by k grids in the graph of degree at most d. That's what we want to have an algorithm for. And the way we're going to proceed is we want to mark one corner of each grid red. So now we have these 2 red corner points of each grid. And the first case is we look for a grid where the 2 corner points have distance at most 4k of each other. So if you have a grid and the corner points have distance at most 4k of each other, then we know here this diameter is at most 2k, this diameter is at most 2k, which means the diameter through the whole graph is at most 6k. So this is now like finding a subgraph with within neighborhoods of radius 6k. And this is something we can do in time n 6k of v to the, what is it, something like O of k squared by enumerating all neighborhoods. So the case where the 2 grids that we're looking for are very close to each other, that case is solved. We can do it in using brute force, using the same approach that we talked about earlier. Which maybe makes the second case more interesting, where we assume that the red corner points of our grid have distance larger than 4k. And what does that mean? And how we're going to solve it? We're going to consider each grid one by one. First, we're going to only look for single grids. So we mark a vertex red if it is the corner point of some grid. So then here, for example, this vertex has been marked red because there exists a grid in the graph where it is a corner point of. And in this example, there would be like these 4 grids would be in the graph. So now we've marked some vertices red. And next we're going to use our R scattered set as a tool. So if there is 2 red vertices with distance larger than 4k, if we have such red vertices and the distance is larger than 4k, what does it mean? It means that the grids of these 2 endpoints, they're disjoint. because every vertex, we have these two red points, they have distance larger than 4k, but every vertex in the grid has distance at most 2k from the red point. And here it is also distance at most 2k from the red point. So the grid can only go up until here, and the other grid can only go up until here, and they will not overlap. So now the problem of finding two disjoint grids amounts to finding two red points with distance larger than 4k. And that's basically the scattered set problem that we talked about earlier. And we can use it, solve it using the same brute force approach. So in a sense, we solved the problem of finding local things, we solved the problem of finding far apart things, and we decomposed our grid problem into a combination of both. We make the case distinction, either it is local or we can split it into things that are far apart. And this approach can be extremely powerful because we cannot only do it for grids, but we can do it for the whole first order logic. You can also split first order logic formulas into this kind of local and far apart subproblems. And the way we're going to do it is as follows. We need some definitions first. So we're going to say a formula is R local if the truth value on a graph G at the vertex V of the graph depends only on the neighborhood of the vertex. So the formula omega is R local if the fact that G models omega on a vertex V. This is equivalent to saying G models omega for vertex V, where we induce G only on the R neighborhood of the vertex. So formula is R local if, in order to evaluate the formula on a vertex on a graph, it is sufficient to only consider the R neighborhood of the vertex. And we require this for any graph G and for any vertex V. If this holds for an arbitrary graph and an arbitrary vertex in the graph, then we call this an R local formula. And here's, to get familiar with the definition, let's check whether some of these formulas are R local. So who can tell me whether this formula is R local that checks whether X has some neighbor Y? It is R local. Why is it R local?
I think R equals 1.
Yes, so in order to check whether X has a neighbor Y, it is sufficient to look within the one neighborhood of our vertex X. If there is a neighbor, then of course it is by definition contained in the R1 neighborhood. So this formula is 1 local. How about this formula? There exists a vertex Y that is not adjacent to X. Is this R local? It's not R local because it could be that the graph maybe looks like this. Within it is a star, and within whatever neighborhood you take of this vertex V, everything is connected to V. But maybe there's another vertex out there, Y, that is not connected to V. And now, even if we take a very large radius around V, it's still only going to contain this part here, and will never contain Y because Y is disconnected from V. So this is not R local for any R. Now let's talk about the examples that we had already. What if omega says that X is the corner of some K by K grid? Would that be local? Yeah, maybe 2K neighborhood. So if X is the corner of some grid, and the grid has diameter at most 2K, so the grid needs to be contained in the 2K neighborhood of V, and is sufficient to evaluate this formula then on these neighborhoods of the vertex. On the other hand, what if we also require that there's a second k by k grid that is disjoint to the first grid? Then it's again a no instance, because even if the vertex here is part of the grid, it could be that there's a second grid that is isolated from the first one, and no matter how far we increase the radius, we're never going to find the second grid. So this is what we call an R-local formula. And of course, you can evaluate these R-local formulas efficiently using the same approach that we did already. Show that you can, on graph with degree at most d, you can evaluate R-local formulas with the running time d to the r+1 times the length of the formula times n. And the way we're going to do it, so we're just going to enumerate all vertices v. And by the property of R locality, you don't need to evaluate phi on the whole graph. We can instead evaluate it on the R neighborhoods of this graph. And each R neighborhood is bounded in size. Its size is most d to the r+1. And then you can do brute force search again. So if a graph has k vertices, then in the last lecture we saw how to evaluate first order formulas in running time k to the length of the formula. And since k is d to the r+1, this gives us the running time that we claimed here on top. So evaluation of these local formulas is pretty easy on bounded degree graphs, but these local formulas are not the only ingredient to first order model checking. So next, we're going to define basic local sentences. They use the R local formulas as a as a tool in the definition. So let's assume we have omega as some R local formula. And additionally, we assume we have some formula dist x1, x2. And this is the first order formula that expresses that the distance between x1 and x2 is greater than 2r. So such a formula exists. We can just say there exists 2r vertices between x1 and x2. So you can say the existence of a path in first order logic, and then you just negate it, and then you have the property that no path between the two of them exists, which means their distance is larger than 2r. So this distance formula can be expressed in first order logic, and we're going to use this as a shorthand for this formula. And now we can define our basic local sentences. So a basic local sentence is a sentence of this form. We say there exists x1 to xs, such that the pairwise distance should be larger than 2r. And additionally, each of those vertices should satisfy the local property omega. So this these local sentences, they express that there should be vertices that are reasonably far apart, and each of them should satisfy a property omega. And omega is now a local property. So an example of such a sentence would be there exist S vertices which have degree at most 4. Degree at most 4 is a local property, and they have pairwise distance larger than 10. This is just an example of what such a local formula could look like. And if this definition is clear, we would come to our final very important building block in our model checking algorithm, and this is Gaifman's locality theorem. It states that every first order sentence is equivalent to Boolean combination of basic local sentences. And to make it algorithmically usable, you can even show that if you're given the first order sentence, you can also compute this Boolean combination of basic local sentences. And what do I mean by Boolean combination? Just like, Boolean combination, you can say this sentence needs to hold, and that sentence should not hold. And if sentence X holds, then also sentence Y should hold. So any Boolean combination of such sentences. And here's an example. So let's try to come up with such a Boolean combination of local sentences. So we know that you can express in first order logic that there's two disjoint k by k grids. And by this Gaifman's locality theorem, there should be a Boolean combination of basic local sentences that is equivalent to the property that a graph has two disjoint k by k grids. Can you come up with such a combination?
The local property would be this 2k local property of the existence of a k by k grid, and then the distance between these two corner vertices that you require would be 4k. That would be the this just greater than 4k.
Yeah, so that's part of the combination, exactly. So either you can say that there exists a single vertex that has such a 6k local subgraph. So you can either say there exists a vertex, and this is part of two disjoint grids that are connected by some path of length at most 4k. Most 4k. So this would be one local sentence. It's a bit simple, this local sentence, because it only talks about a single vertex, not multiple vertices, while before we said this local sentence could mention many vertices that are far apart. And the other one is there exists two vertices S1, S2, which are both part of such a grid, and their distance is larger than 4k. And in the proof before, we saw that this is a complete distinction. If such a grid exists, either it is contained in this 6k radius, or it is they're far apart, and then the grids can't overlap. So here we see how to break such a formula down into a Boolean combination, and you can do this for any first order sentence. So let me talk a little bit about the constants in this locality theorem. So if you have a formula phi, and it is a Boolean combination of basic sentences, and these sentences have a radius r, right? And you can show that the radius r is at most, I think, 2 or 3 to the phi. So the radius r of the local sentences, it depends exponential on the formula that you're working with. So in our case, it would be exponential in k roughly, because k is a grid size there. So this is the good news. So the r is only exponential. However, the number or the length of the Boolean combinations, it will be again a tower function. So if you have some formula phi, then the Boolean combination will be, in the worst case, it will have a length of 2 to the 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 2, and the height of this tower will be phi, or the length of phi. So these Boolean combinations, they can get very, very long in the worst case. But since we are more interested in the theoretical classification, we're just going to use it as a black box, and still doesn't change the fact that for every formula, there is a Boolean combination. Except just that it blows it up, the function f, a little bit that we usually have in front of our running times. So let's now prove our result by Caesar. So we're gonna want to show that you can do first order model checking in running time f of phi times n on bounded degree graphs. And so now we're going to use Gaifman's locality theorem, and states that phi is equivalent to a Boolean combination of basic local sentences. So this means that in order to evaluate phi, we can instead evaluate all the basic local sentences, and then we know which ones are true and which ones are false. And then we can evaluate the Boolean combination of these sentences. So if the Boolean combination says basic local sentence 1 needs to be true, basic local sentence 2 needs to be false, for example, then this is something that we can easily check if we have evaluated each of those sentences. So from now on, we only need to evaluate these basic local sentences. And this number S here, and this radius R, and this formula phi, it will depend only on our input formula, phi. So we can treat them as a function of the formula length, these values. So let's try to evaluate such a Boolean, such a basic local sentence. So the first thing we're going to do, we're going to find all vertices that satisfy omega. Remember, basic local sentence, we need to find vertices that are far apart and that satisfy omega. So let's first find all those vertices that satisfy omega. And we already saw how to do that. We only need to evaluate omega on the R neighborhoods of the graph. So we can, and these R neighborhoods have bounded size. We can therefore enumerate all vertices and check whether omega holds on the R neighborhood of this vertex. Our locality says the formula holds in the R neighborhood if and only if it holds in the whole graph. So that's why we can restrict ourselves to looking within the R neighborhoods. And you can do this using brute force in the running time that's nicely bounded. And you do it for all vertices V. And now we find all the vertices that satisfy omega. And let's color these vertices red. So the basic sentence says that there exists x1 to xs such that the distance pairwise is larger than 2r, and the vertices are colored red. Because we colored all the vertices red that satisfy omega. So in other words, we need to find a red 2r scattered set of size s. Remember, 2r scattered set means the distance pairwise are larger than 2r, and this is the requirement that we need to satisfy here. And we already, early on, we discovered how to compute r scattered sets or 2r scattered sets. So this is another thing we can do in running time, some function of r and s and n. And since r and s depend only on phi, we get a nice running time f of phi times n. And this already completes the proof of Caesar's theorem. Other questions about this so far? Nothing in the chat either. Then I guess this completes the case of bounded degree. And next, we want to generalize this to locally bounded tree width. And before we do that, we first need to define what locally bounded tree width actually means. So locally bounded tree width basically means that the tree width of every radius neighborhood is bounded as a function of the radius. So it states the graph class has locally bounded tree width if there exists a function g of r such that for every graph in the graph class and every vertex of this graph and every r, the neighborhood has tree width at most gr. So we take an r neighborhood within our graph from the graph class, and the tree width of this r neighborhood, it should depend only on the radius r. So this is a generalization of bounded tree width. So for bounded tree width, the tree width of the whole graph should depend only on some value of the graph class, but now we also allow it to depend on the radius of the subgraph that we're taking. So let's consider some examples. So here we have the class of all grids. Does the class of all grids have locally bounded tree width? We have to check whether every neighborhood, the tree width of every R neighborhood depends only on R. So let's take an arbitrary R neighborhood. So we pick a vertex, and every vertex with distance at most R from it. So here, this is R, and we notice that this is contained in a subgrid with at most R squared vertices. So for a grid, you could set G of R equal to R squared, because every R neighborhood contains only R squared vertices, and therefore the tree width is also only R squared. And actually, you can reduce this to G of R equals R, because the tree width of an R by R grid is R. So this shows class of all grids has bounded degree and therefore also locally bounded tree width. And you hopefully also notice that bounded degree implies locally bounded tree width. So here's another example. The class of all grids where there's a vertex extra that is connected to one column of the grid. So now we have no longer bounded degree. Does it still have locally bounded tree width? I would say yes, because if we take a look at an R neighborhood of this graph, then it can contain, in the worst case, this vertex here, and maybe everything to distance R. So here, this is distance R. And now we have like an R by N grid, and an R by N grid has tree width at most R. So like you get such a narrow slice of a grid, and the tree width of this grid is bounded by the width of the smaller length, and the smaller length is R. So even here, the tree width is bounded by a function of R, or exactly R. And such a thing would have also locally bounded tree width. What about the more extreme case, where we add an apex vertex that is connected to everything? Do we still have locally bounded tree width? I guess not, because now every vertex has distance 2 from each other. So the 2 neighborhood of a vertex would be the whole thing, and the whole thing contains very large grids, so it has unbounded tree width. So this no longer has locally bounded tree width. And the relationship to other graph classes looks like this. So we saw already that it generalizes on the tree width, it generalizes on the degree, and it also generalizes planar graphs. So locally bounded tree width generalizes basically everything that we introduced already. And you can see this like this. So for planar graphs, you can show that the tree width of a planar graph with radius r is at most 3r minus 1. So in planar graphs, this means R neighborhoods have radius at most 3r minus 1. So their tree width is bounded linearly by R, and they have locally bounded tree width. Similarly, for bounded degree graphs, the R neighborhoods have size at most d to the r plus 1. So in particular, also their tree width is bounded by d to the r plus 1, because the tree width cannot be larger than the size of the graph. So this is very nice. And let's turn towards a little bit stranger example of a class with locally bounded tree width. So let's take a clique of size n, or for every n, we define the class as follows. It contains a clique of size n after we subdivide every edge log n times. So the class of log n subdivision of cliques of size n. We have here n vertices, and we replace every edge with a path with n vertices, with log n vertices. So this class also has locally bounded tree width. And how do we prove that? So let's take a look at a circle in this graph. So every circle has length at least 3 times log n. Because if you're shorter than 3, you start anywhere, and if you want to go anywhere, you have to pay at least log n vertices to come to the next vertex. And the only way to make a circle is by passing through another log n vertices to go here, and then maybe another log n vertices to come back. So there are no short circles in this graph. Every circle has length at least 3 log n. And what does it mean? Let's take a look at a neighborhood with radius at most log n. So a neighborhood with radius at most log n, it can contain no circle because circles have longer radius. So the neighborhood is a tree and therefore has tree width at most 1. So if you look at any vertex here and you only go at most log n steps, the only thing you get is like this kind of tree. On the other hand, and now it gets interesting, what if R is larger than log n? Then we don't know anything. The tree width can be n. But n is then bounded by 2 to the r. So, and this is now very nice. So if r is larger than log n, then the size of the graph and therefore also the tree width is bounded by 2 to the r. And this completes the picture. So with this case distinction, we know that for every r, the R neighborhood has tree width at most 2 to the R. So this proof feels a little bit like cheating because we're not doing anything, we're just making a very simple case distinction, but it does what it's supposed to do. The tree width is bounded by 2 to the R. So now we have a bit of a non-trivial class that does not have bounded degree, it is not planar, doesn't have bounded tree width, but it still has locally bounded tree width. And I guess we have 10 more minutes, maybe we can even complete the proof. So the last final result is that you can do first order model checking also on locally bounded tree width classes. So this is a very nice and very general result by Frick and Bohl, and states that for every epsilon, you can decide whether the formula phi is true on a graph G with locally bounded tree width with a running time that is a function of epsilon and phi times n to the 1 plus epsilon. And this looks very strange, and I recommend you to ignore the epsilon for now. So if you set epsilon to 1, then you get a function of 1 and phi times n to the 2. So you definitely get an FPT running time, and the epsilon basically only means that you not only get a quadratic algorithm, you also get an n to the 1.1, you also get an n to the 1.0000001. So basically you can get as close to linear time as you like. The price that you have to pay is that the function f, the function growth with epsilon. So if you want to decrease the running time in n, then the running time in phi increases. So we're not going to show this this epsilon version, just going to show this basic version where epsilon is 1. So we want to evaluate the formula phi in time function of the formula length times n squared. And we want to use Gaifman's theorem for it. So again, in order to evaluate the formula phi, we can decompose it into a Boolean combination of basic local sentences. And again, it is sufficient to evaluate these basic local sentences to decide whether the formula is true or not. So far, just like the bounded degree case. But now we diverge a little bit. So we have to evaluate such a basic local sentence. And we again want to compute the set R, which contains all the vertices for which omega holds. So again, we want to build the set of R vertices that satisfy omega, such that afterwards we can find an R scattered set in the graph. Okay, so far still like the bounded degree case. So how do we find our set R of vertices that satisfy omega? So remember that the localized for the local formula, we don't need to evaluate them on the whole graph. We can evaluate them within the R neighborhoods. And the R neighborhoods in G, since we have locally bounded tree width, they have tree width at most G of R. So we can enumerate over all vertices and check whether this neighborhood satisfies omega using Cosell theorem, because the tree width is bounded. So the running time that we get is some function of omega and some function of the tree width, which is bounded by G of R times n, because the neighborhood is size at most n. And we not only have to do it for a single vertex, we have to do it for all the vertices. And this is where the quadratic factor comes in, because for every vertex, we have to use Cosel's theorem. And if you analyze it naively, you get running time that is n for every vertex, so n squared in total. If you analyze this a little bit more carefully, you get this n to the 1 plus epsilon. But we don't bother with that for now. So now we have the set of all vertices colored red that satisfy omega. And what we do next, we have to find a 2R scattered set of size S in G, or we have to decide that such an R scattered set does not exist. And what we can do is we can restrict ourselves to the R neighborhood of our set R, because if we have two red vertices and we draw the balls with radius R around them, if their distance is smaller than 2R, then it's also smaller than 2R in the graph where everything else is deleted. So it is sufficient to find a 2R scattered set in the R neighborhood of our set, capital R. Because vertices that are further apart from our red vertices R, they cannot be part of a path of length at most 2R between two vertices. So if they have distance at most 2R in this graph, then they also have this large distance in the whole graph. And this is why we're going to consider only this neighborhood of the set capital R. And we're going to do a case distinction on the neighborhood. So we assume that our graph either has diameter at least 5 SR. So if the graph has diameter at least 5 SR, then there exists a shortest path of length 5 SR. That's the definition of a diameter. And we can pick vertices on this shortest path. And by picking a vertex every 5R steps, we can find these vertices pairwise at every 5R steps. And there's going to be S of them, I think. And since all these vertices have distance 5R from each other, they're reasonably spaced far apart. Additionally, since we're only looking at the R neighborhood of the red vertices, every one of them has a red vertex with distance at most R from them. So there's always a red vertex that is at most R steps apart from these vertices on the path. So this means that any two red vertices have distance larger than 2R, because the whole step has size at least 5R, and each arm has size at most R. So the difference is at least 3R, which is larger than 2R. So we find these S vertices that are 2R scattered, and if the diameter is large, we always have a yes instance. On the other hand, if the diameter is bounded by at most 5 SR, then we can use Cosel's theorem again. So we have a graph of bounded diameter, and we want to find an R-scattered set. This is expressible in first logic or MSO logic, and then we can just use Cosel's theorem to decide whether this graph here of bounded tree width contains a 2R scattered set. Because the radius is bounded, therefore the tree width is bounded, and we can use Cosel's theorem, and that's all we need to do. And this completes the proof. So we have not only meter theorem for bounded degree graphs, we also actually have it for locally bounded tree width, and this generalizes bounded tree width, planar graphs, bounded degree, and this is a very nice result. If you're looking for negative sides, then maybe it's not such a robust result, because if you add an apex vertex to the graph class, then suddenly everything is connected to everything, and locally bounded tree width is basically the same as normal bounded tree width. So locally bounded tree width is not very robust under adding apex vertices. But other than that, I think it's a very nice result. And this brings me to the end of the lecture. Are there any questions? Questions online? If not, then thank you all.